Hey everybody, welcome back to chemistry. And now what we're going to be doing is going to calorimetry. So what calorimetry is about is it's the theory and practice of figuring out what the change of energy of a chemical reaction is. And so let me give you an example of something that calorimetry would tell you. So we have that chemical reaction there on the screen, which is the combustion of methane, which is the molecule CH4. And you can see that that molecule, methane, reacts with oxygen, and then it produces the products carbon dioxide and water. And so using the technique of calorimetry, you can figure out, for example, that the heat released in that chemical reaction per mole of methane, which is CH4, is 891,000 joules. So how do you go about figuring out what the heat of a reaction is? Well, the way you do that is you need a device called a calorimeter. And so there are two different kinds of calorimeters I need to talk about. So one kind of calorimeter which you need to know something about is something called a constant volume calorimeter. And so an example of that would be something called a bomb calorimeter. And importantly, what the constant volume calorimeter tells you, it tells you the change of an internal energy of the reaction. Now there is another kind of calorimeter you may use, and this is called a constant pressure calorimeter. And so an example of that would be a coffee cup calorimeter. And so a constant pressure calorimeter tells you what the change of enthalpy of a reaction is. Okay, so what I'm going to do first is talk about how we go about using a constant volume calorimeter. So we have this bomb calorimeter here. So I need to go over to the computer and describe it to you. So here is a picture of a constant volume calorimeter. And so the example of the constant volume calorimeter we're looking at is a bomb calorimeter. And so the thing to sort of notice here in this calorimeter is that here inside the calorimeter, you basically have this can here, which is highlighted in this red rectangle. And so that can is called a bomb cell. And it's important to keep in mind that the walls of the can are very strong. They are made of reinforced steel. The can walls are so strong that there will be no change of volume as you're carrying out this reaction. So how do you go about using this calorimeter to figure out a heat of reaction? So what you do is as follows. You have the bomb cell and you have it out of the calorimeter, and then what you might do is in some fashion load the bomb cell with reactants. So with the previous reaction we were looking at, the reactants were methane and oxygen, so you can add them to the bomb cell there. What you would next do is put the lid on the bomb cell, and then you put it into the calorimeter housing and connect it into wires. Now, after that, you have to cover the bomb cell with water. And then once that calorimeter is full of water, you close the lid of the calorimeter. And so there are some kind of things that you can sort of see that are part of the bomb calorimeter. So one thing that you can see is that there is a device for measuring the temperature of the water. It is here. So this probe here is called a thermocouple, and the thermocouple is connected to a digital readout of the temperature. And also you have a device that steers the water around. The goal of that is just to make sure that any heat released by the bomb cell will be evenly distributed throughout the water. Next, what you would have to do is start the reaction. And so what you might do is you might have some kind of device here. We have some fuse wires here. And then that will send a discharge across the bomb cell. And then the discharge may be enough to get the reaction going. And then the reaction goes to completion. So when that happens, when the reaction goes, it's going to produce a lot of heat. And so what will happen is the heat will leave the bomb cell and go into the water of the calorimeter. Now, what you really want to figure out is how much heat is being absorbed by the water in the calorimeter, because that will tell you how much heat is being generated in the chemical reaction. So how do you go about finding the heat absorbed by the water in the calorimeter? Well, what you do is you take a final temperature of the water after the reaction is complete, and subtract from it an initial temperature of the water before the reaction started, and that will give you the change of temperature of the water there. To figure out how much heat was absorbed by the water, what we do is we make a calculation that is based on not so much only that the water is absorbing heat, but also the whole calorimeter along with the water is absorbing heat. Now, most of the heat will be absorbed by the water, but a little bit of the heat produced by the reaction will be absorbed by the calorimeter housing. So what we do is we indicate the amount of heat being absorbed by the water and the calorimeter housing with this letter here, Q cal/water. And so what is that going to be equal to? Well, if you take the temperature change of the water and then you multiply that by the general heat capacity of the calorimeter water system, that will give you the heat absorbed by the calorimeter water system. Now, once you figure out the heat absorbed by the calorimeter water system, that tells you the heat released by the chemical reaction in the bomb cell, because we're assuming here that any heat here generated in the bomb cell is going to be absorbed by the water and calorimeter. Now, here is sort of this equation that describes this. And so any heat absorbed by the calorimeter and the water, we take the negative sign of that, and that will give you the value of the heat produced by the chemical reaction. One thing I want you to notice is that here we have heat described with a subscript V. And the reason why we're doing that is because we're doing this reaction at constant volume. And so to indicate we're looking at heat at constant volume, we write QV there. So another thing you can do is generalize this a little bit by describing what a system is, a surroundings, and a boundary. So the system is everything within the bomb cell. That's where the chemical reaction would be. And so you can think of the surroundings as everything outside of the bomb cell, but still within the can of the calorimeter. So the surroundings would include the water of the calorimeter and would also include the metal housing of the calorimeter. And now we also have a boundary, and the boundary would be just the steel wall of the bomb cell. So again, the goal of bomb calorimetry is to make sure any heat lost by the system will be gained by the surroundings. We see this represented by this equation here. One thing we just talked about is that the system, which is the chemical reaction, the heat lost by the system will be called QV, and the reason why we're calling it QV is because the bomb cell has a constant volume, and this is going to be equal to any heat absorbed by the calorimeter and the water, which I've marked there. You probably want to find out what QV is. And so if you know Q cal water, you can figure out QV. How do you figure out Q cal water? So all you do again is take the general heat capacity of the calorimeter water system and multiply it by the temperature change of the water. So your goal in bomb calorimetry is find the heat at a constant volume. And the reason why you want to find that is because the heat at constant volume is equal to the change of internal energy of the reaction. So I want to go over here to the glass board and explain that. Okay. So one of the things you learned about previously is when you have the change of internal energy of the system is going to be equal to the heat plus the work. Now, here the system is the chemical reaction that's in the bomb cell. And so what I can do is just say, all right, the change of internal energy of the chemical reaction is going to be equal to the heat of the reaction plus the work of the reaction. All right. Now, let's think about what the work of the reaction is. And so maybe one of the things you remember is that when you have work, it's going to be equal to negative pressure times the change of volume of the reaction. So we can rewrite this and we can say, well, the change of internal energy of the reaction is going to be equal to the heat of the reaction minus P delta V. Now here's where things get a little bit interesting. And so this chemical reaction is occurring in a bomb calorimeter. And so the walls of the bomb calorimeter are very strong. And so during the reaction, the change of volume is going to be 0. So you can see here that this term here, P delta V, is going to be 0. Okay, so how does that affect things? Well, what happens is this. When this happens, what will happen is that any work that is naturally made in this reaction is going to be converted to heat. So we can write something new here. We can say that the work of the reaction plus the regular heat of the reaction, they will be basically added together to form a total heat in the bomb calorimeter. And we call this total heat at constant volume. And so just to say again, this only happens in a bomb calorimeter when the change of volume is equal to 0. So only in bomb calorimeter. Okay, so this may seem kind of strange in that maybe if you have a chemical reaction at normal conditions, say constant pressure, then that chemical reaction may produce some heat and may generate some work. But here, if the same reaction is in a bomb calorimeter, something interesting happens. That work that naturally occurs in the chemical reaction is changed over to heat, and it's added to the regular heat of the reaction that is occurring to give you a total heat now. And so we call this a heat at constant volume. So what you can see now is that the value of heat for a reaction can change depending on the circumstances. And so this is consistent with what we learned before. You may remember that heat and work are so-called path functions and that their values can change depending on the circumstances. Also, the work is changing. If you had this chemical reaction at constant pressure, it might be doing some work. It has a value for work, but then in the bomb cell, all that work is be converted to heat. And so in the bomb cell, work really is 0 because it's all been converted to heat. So the work is a path function. It's changing too. So now let's move on with this. And so let's figure out whether QV here is going to be equal to the change of enthalpy of the reaction or the change of internal energy of the reaction. It's going to be one of the two. So let's figure out what it is. Okay, so here is how I think about it. So here is the change of internal energy of the reaction, and it's going to be equal to the Q of the reaction plus the W of the reaction. But we learned that when we're having this reaction occur in the bomb calorimeter, again, all this W of the reaction is going to be added on to the heat of the reaction. So those two terms in a bomb calorimeter are added. So now what we get is after we add these joules from the work and the heat, we now get a total heat, which is QV. So you can see that here the total heat, the heat at constant volume for this chemical reaction is going to be equal to the change of internal energy of the reaction. Okay, so now what I want to do is sort of do a problem that you might see on your homework or on a test related to determining energies using a bomb calorimeter. So let me go on to this next slide here. Okay, so the problem reads as follows. When 1.01 grams of sucrose, and we're given the molar mass of sucrose, undergoes combustion in a bomb calorimeter, the temperature rises from 24.92 degrees to 28.33 degrees Celsius. Find the change of internal energy of the reaction for the combustion of sucrose in kilojoules per mole of sucrose. The heat capacity of the bomb calorimeter determined in a separate experiment is that value, which is 4.90 kilojoules per degree Celsius. Okay, so in the end here, what we're trying to find is a change of internal energy for the combustion of sucrose, but we have to get this in kilojoules per mole of sucrose. Okay, so how do we do that? Well, let's first sort of draw out what is going on in this problem. So we have a bomb calorimeter, so I'm going to try to draw that. So here is the can of the calorimeter, and within the can of the calorimeter we have a bomb cell. So we have the bomb cell, so let me write B, C for bomb cell. Okay, and so you might remember that the bomb cell is surrounded by water here. Okay, so what is going to happen is that you are going to carry out a chemical reaction with this bomb cell. And you know, as the chemical reaction is occurring, the volume is not changing. So all heat leaving this chemical reaction is going into the water and into a little bit to the calorimeter housing. Okay. Now, another way we can sort of look at this is we can think of sort of the, within the bomb cell as being the system here, and then outside of the bomb cell is the surroundings. Okay, so let me write a few useful equations here. So in general, we can always say is that the heat of the system is going to be equal to the negative heat of the surroundings. So what is the heat of the system? Well, you might remember from the previous slide that the heat of the system is the heat that is being produced by the reaction at constant volume. So I'm going to write QV is equal to negative Q of the surroundings. Okay. Now, what is the Q of the surroundings? Well, the Q of the surroundings, you might remember from the previous slide, is going to be equal to the general heat capacity of the water and the calorimeter times the temperature change of the water. So we can write here, QV is equal to negative general heat capacity of the water calorimeter times the change of temperature of the water and calorimeter. Okay, so if we know the general heat capacity of the calorimeter water, which we do in that problem, and we know the temperature change, which we can figure out, then we can figure out what the heat at constant volume for this chemical reaction is. Okay, so let's go ahead and do that. So the heat capacity of the calorimeter is 4.90 kilojoules per degree Celsius. Okay, and we're going to multiply this by the temperature change, so let's work this out. The temperature change of the water is always going to be equal to the final temperature of the water minus the initial temperature of the water. Okay, and so the final temperature of the water is 28.33 degrees Celsius minus 24.92 degrees Celsius. So let me work out that value here. So it's 28.33 minus 24.92, and I get 3.41 degrees Celsius. Okay, so we put in 3.41 degrees Celsius here. And so one thing that you can see is that the degrees Celsius will cancel out, and so it leaves kilojoules in your answer, which you carry in. So it's 3.41 times 4.90, and I get 16.709. We'll just use all those digits. So negative 16.709 kilojoules. Okay. Now, one of the things that you might remember from the previous slide is that when in a bomb calorimeter you figure out what the heat of the constant volume is, that is the same as the change of the internal energy of the reaction. So this value here is equal to the heat of constant volume, which is the change of internal energy of the reaction. So I'm going to write delta U of the reaction here. But here's the problem. We have the change of internal energy of the reaction in kilojoules, but we got to get this into kilojoules per mole of sugar. So how do we do that? Well, this is what you do. You take that value and you note in this problem that this amount of change of internal energy occurs with that mass of sugar you see in the problem, which is 1.01 grams. So I'm going to write 1.01 grams here. Now, can we figure out how many moles this is? Sure. And so what we can do is just multiply this by the molar mass of the sucrose, which is 342.3 grams over 1 mole. And so I think you can sort of see now is if we were to do that calculation, the grams cancels out. So what you would do is multiply negative 16.709 times 342.3 divided by 1.01, And then that should give you an answer in kilojoules per mole. And so the number here is going to be negative 5.66 times 10 to the 3 kilojoules per mole. This is rounded to the correct number of significant figures. Thank you for listening to that, and we'll see you next time.